There we go. We're live now. And away we go. Okay, so does 0.9 repeating equal 1? And this seems counterintuitive for a lot of people, but the answer is actually yes. And some people would say, well, wait a minute, it's not quite 1 because it's smaller, right? It's smaller if you think about it. I mean, 0.9 repeating, of course, so hopefully everybody recognizes that symbol. That means, of course, 0.99999. It's hard for some people to get their head around the idea that, well, it's not exactly 1. Otherwise, why don't we just say 1? Well, hopefully there's a couple of ways I could convince you. There's actually lots of different ways mathematically to prove that these two numbers are the same number. But maybe I can just convince you with kind of just a reasoning argument. Like, for example, do you know what 0.1 repeating's fraction equivalent is? Anybody? And at home, when I ask an open question, feel free to chime in. Remember, when I record, I'm not actually recording my Teams meeting, so your name doesn't pop up. You'll hear your voice on the video or whatever, but you could also answer questions in Teams right now. The chat is going. That's right, this is 1/9. Somebody got it right away. And what is 0.2 repeating? 2/9. And what is 0.3 repeating? Logically, it's 3/9. And 0.4 repeating is 4/9. And I'll just say etc. So by that pattern logic, 0.9 repeating must be 9/9. But look at that. What's 9 divided by 9? So there you go. So there's just a very basic argument. I can give you a more sophisticated one that should make sense to you if you think back to the first unit you did last semester. I'm assuming everyone here was in 30S pre-cal last semester. So do you remember Unit 1? Unit 1 was, of course, sequences and series. I could take 0.9 repeating and think of it as, of course, 0.99999, blah, blah, blah. And I could actually think of this as 9/10 plus 9/100 plus 9,000. Okay, we'll take a quick break here for O Canada. Okay, and we're back. Okay, I heard somebody saying something on messages. What was it that I missed as I couldn't hear over the treaty announcement? There was a question about what I was doing? Okay, for those of you who at home just joined us, this is a notes handout that you can just jot the notes down quickly. You'll get the actual handout on Tuesday when you come in, so just maybe do the notes roughly and then you can fill them in later. My apologies. I had them sitting here on my desk and I forgot to actually hand them out to you. But guys in the room, of course, they're sitting on your desk waiting for you, huh? All right, so like I was saying, 0.9 repeating is 9/10, 9/100, 9,000, plus that one would be 9/10,000, etc. And remember Unit 1? That should look familiar. What kind of a series is this? Don't all answer at once. Sorry, what kind? It's a geometric sequence, right? It's a geometric series, and it's a geometric series with an R value of 1/10, right? Every number here is 1/10 smaller than the number before it, or 1/10 times as small as the number before it. So remember that you can sum an infinite series if the R number is between -1 and 1, because that means it's getting smaller to infinity. And I don't know if anybody's good at remembering formulas. I'm kind of bad at it, but I've done this formula enough that I should remember it. It's T1 over 1 minus R. That ring a bell from back on the formula sheet in grade 11? So the first term is 9/10 all over 1 minus 1/10. And look at that. What's that going to look like? What's 9/10 divided by 9/10? So there you go. Two ways. The first one just being kind of common sense and fraction decimal thinking. And the second one, this one's almost like a proof, really, that 0.9 repeating is mathematically the same number as 1. And that's a very important idea if you're going to start studying calculus. You have to get your head around the idea that as you get infinitely close to a value, you are that value. And why is that important? Well, if you watch the video that I put a link to on the blog last night, Professor Dave talks about something that bothered the ancient Greeks very, very deeply. They called it Zeno's paradox. If you, for example, have a distance in a room that's 2 meters long, well, of course, you could cut that into a 1 meter chunk, and then, of course, 1 meter on the other side, and then, of course, you could cut that into a 1/2 a meter chunk, and then a 1/4 of a meter chunk, and then a 1/8 of a meter chunk, and you could keep cutting it in half forever. So if all of these fractions go on forever, how on earth could you ever start here and walk your way down 2 meters and get to here? How is it even possible? You have infinite fractions to get through. And that's why they called it Zeno's paradox. But of course, once again, using this wonderful idea that you can add the fractions 1 plus 1/2 plus 1/4 plus 1/8 to infinity, and no problem, run it through this formula and you get 2. No paradox about it, as long as you can handle the idea that just because you're adding infinite things doesn't mean you're getting an infinitely big number, especially if the numbers are getting smaller and smaller as you go. So that's an important idea in many branches of math, and it's especially important here in calculus. This looks like I'm changing gears very severely, but I'm actually not. First of all, this has a typo on it. Can you actually change this to x minus 3? That's supposed to say minus 3, not minus 6. So let's look at, well, actually, we're going to look at the graph of it second. Let's play with it algebraically first. If I had to divide those two things, what would be the first thing I'd do? And some of you are going, oh, let's use our fancy new long division that you taught us the other day. No, this one we have a simpler tool in our toolbox. In fact, it's the tool you should almost always try as one of the first things you look at. What can you do here? Yeah, you can factor the numerator. If you factor the numerator, you get x minus 3, x minus 2, and of course, a number divided by itself is 1. So mathematically speaking, these two equations are what you call equivalent equations. Right? They are actually the same as each other, really. They're equivalent equations. Now, having said that, they're not quite identical, are they? Let me get a highlighter here. There we go. This is a rational equation, and of course, this is just a linear equation. And the rational equation has something that the linear equation doesn't. It has an NPV. Do you remember what NPV stands for? It has a non-permissible value. You see, in this equation, if I say, let's turn them into functions. If I say, come on, pen. If I say f of x is equal to x minus 2, f of 3 is just 1, right? No problem. But on my other equation, if I have, again, I'll make it a function. If I have this function, which I do know algebraically is equivalent, check it out, f of 3 here doesn't exist because, put it on the top, no problem. I get 9 minus 15 plus 6, right? No problem. What's 9 minus 15 plus 6? Well, 9 minus 15, I get 0, right? But on the bottom, I also get 0. And 0 divided by 0 doesn't really exist, right? Right? In any branch of math, in all branches of math, division by 0 is not allowed, ever. This is one of those, I know, as a math student, you might not want to believe me on this one, because we've lied to you before. Your grade 1 teacher, if you accidentally wrote down 5 minus 6 instead of 6 minus 5, they said, oh, you can't subtract a bigger number from a smaller one. Well, of course you can. Welcome to integers. And if your grade 3 teacher is teaching you division and you wrote the division backwards, and instead of 6 divided by 2, you wrote 2 divided by 6, your teacher probably said, oh, you've got that wrong, you can't do that. Well, of course you can. 2 divided by 6 is a third. No problem there. And even in grade 8, when we told you couldn't square root a negative, well, you kind of can as long as you're not worried about being in real numbers. That's what imaginary and complex numbers are all about. But this time, you're going to have to take my word from it. We mean it. It is an important idea in this course. It's an important idea in all branches of math. Division by 0 is just never allowed. You cannot divide a number by 0 and get any sort of meaningful numerical result. So, with that in mind, what would the graph of this thing look like? Well, the graph of this one, the linear one, which I know is equivalent, is super easy to graph, right? It starts at -2, the y-intercept, has a slope of 1. So it would do something like this, right? So if I graphed the rational one, shouldn't I get the exact same picture? Well, let's take a look. I'm actually going to put it on Desmos. Let's see, Desmos, where are you? There we are. So let me go back to the home screen. There we go. And, oh, let's bring up the keyboard just to get in my way. Get out of there. Yeah, there we go. That looks pretty normal, doesn't it? It's exactly what I thought it was. But, hold on for a second. Let's get closer to that value when x was 3, shall we? So there's 3.29, 3.24, 2, 1 far, 1, 3, 1, 9, 0.09.087. We're getting closer and closer. Ah, did you see that? I don't, can I point at that with this? Let's see what happens if I point. Yeah, there we go, that's better. So let's see, where was that? There we go. Can you see that? My hands aren't steady enough to hold it there. What's it saying when I am at exactly 3? It's saying undefined. There's an actual hole in this graph. Now, the way that you actually should draw this graph, Desmos doesn't draw like this. But this is the way you should draw a graph like this. You should, let me go back to the graph now, on our notes. There we go. You should, at 3, well, at y is 1, at 3, where you know it doesn't exist, you should actually make a little hole. Something they taught you how to do back in grade 9 when you were graphing inequalities. Remember that? If the inequality value that you're graphing isn't a greater than or equal to or and equal to, you always draw an open circle. Remember that? So that's the way you should draw that. And Desmos will draw it like that too, as long as you go really close to it. So why don't they actually put a little hole in the picture the way that that you can see without having to drag your cursor around? Well, because Desmos does take their cue from teachers, and calculus teachers, I guess, in North America that advised them said, oh, don't make it that easy for students. We want them to be able to figure out where the hole is. Do you understand why there's a hole there? It's because I can't divide by 0. And because I can divide by any other number but 0, Desmos doesn't want to make the hole that big. Because x can't be 3, but x can't equal 3, but x can equal any other real number you like. It could be 2.999999999. It could be 3.000000001. So here's a very important idea in calculus. The idea that in the function f of x equals x squared minus 5x plus 6 all over x minus 3, f of 3 is undefined because I can't divide by 0. But, and this is the wording we're going to learn how to use starting in tomorrow's lesson. I did not mean tomorrow. We are not doing a lesson on Saturday. How about Tuesday's lesson? There we go. Oh, come on, pen. The limit of the function f of x as x approaches 3 is actually 1. And that, you can put a little circle around it or highlight it or do whatever you want, because that's an important statement. And what do I mean by the limit? Well, it's kind of like saying 0.9 repeating is really just 1. Right? If I put in 2.99999 into the function, I get very, very close to y equaling 1. And if I put in 2.999999999, I get even closer to 1. I get infinitely closer to 1. And actually, the same thing would be true if I put in 3.01 and then 3.001, then 3.0001. Whether I come at it from this direction or that direction, I get infinitely close to having a y value of 1. So even though the function doesn't really even exist there, it is there. Okay, let's change gears a little. Look at the next page. I'm actually going to change up this activity a little from the way Mr. Lacko drew it up. I'm going to say instead of 2 ways to draw a disk, we'll draw some disks. Oh, don't you worry, we're going to draw disks. But 2 ways to, how about consider the area of a circle. And there's actually lots of ways to consider the area of a circle, but this is going to be 2 ways. 2 ways to consider the area of a circle. Okay, number 1, what if I make a circle and fill it in, and by make a circle and fill it in, I'm going to say split into wedges. Ever seen this particular argument before? Perhaps your junior high teacher might have told it to you. Of course, you know, I taught junior high for 18 years, and I've met many a junior high teacher who probably don't know this argument. And if you ask them, why is the area of a circle pi r squared? They'll say something like, well, because that's what it says in the textbook and the curriculum guide, and that's what they want me to teach them. But has anybody ever actually tried to convince you that that has to be the argument? Well, if we start with the knowledge, that the circumference of a circle is, let me just write it up here, the circumference of a circle is, of course, remember, good old 2 pi r. Then suppose I take these wedges, and I get fancy with them. I split them into, let's see if I can move this over. There we go, come on. There, haha, there. Oh, look at that. It actually goes behind the lines that I drew. I didn't know that the notebook behaved this way. Okay, so, oops, and then up comes the, oh, that's not what I wanted to do. There we go, I want an eraser. There we go, haha, go away. Get a bigger eraser, There we go. Those lines are in the way now. There. Good enough. Okay, so if you could now imagine that you take all of those wedges, and again, just sketch this, right? If you can imagine that you could take all of those wedges and cut them out, take a pair of scissors and rearrange them something like that, you get something pretty close to a parallelogram. Do you remember how to find the area of a parallelogram? Base times height. Well, what's the height of the parallelogram? It's the radius of the circle, right? Because that's how long it is. That's the distance from the center of the circle to the edge middle of any of those wedges, right? That's definitely r for radius. And of course, the distance around is 2 pi r, it's circumference. And isn't that what this would be? This distance is 2 pi r. And of course, logically, once again, you might have a little bit of a problem with what I just did here, because clearly that's not really a parallelogram. After all, parallelograms have nice straight lines. And this thing, well, that's a curve, and that's a curve, and that's a curve, and that's a curve. But what if I said, let's cut smaller wedges? What if I said, let's cut infinitely smaller wedges? Notice the curvature of those ends kind of goes away. Like here, let me just show you. Notice how much flatter that looks because I cut smaller wedges? And imagine if I did that. Now it's looking almost like a rectangle, which is definitely base times height, which is definitely 2 pi r times r. So base times height is, oh, right, sorry. Thank you. This is half of, oh, come on, eraser. Okay, my eraser's not coming up. There we go. Right, this side's pi r, and the other side is also pi r, right? Because together they'd make the circumference, right? Sorry, yeah. Together those two sides are pi r, which means when I do base times height, I get, of course, pi r squared for area. Okay? So there we go. So there's one kind of, if nobody ever explained to you where the formula for pi r squared comes from, there's one way to do it. Another way, and this way's kind of more fun, what if we draw a bunch of rings? So I'm going to make a thicker marker. I don't know if I'm going to make this work. I've never tried this before. I'm going to make there's a nice thick marker. Okay, I'm going to try to do this real careful. Oh, there we go. Come on, pen. There we go. Oh, there. I kind of goofed that up. There. And then I'm going to do the same thing with a blue one. Come on. Okay, that's not bad. Then I'm going to do the same thing with the red one again. Come on. I'm not trying to leave little white gaps. This is working about as well as I hoped it would. Come on, come on. Of course, my pen just sometimes decides to stop working. I don't know why that is. And then, of course, here. There! All right, I kind of knew that this would be hard to do physically. So once again, I just captured a picture from somewhere. Let me go find it. Where is that picture? There it is. Let me just drag this over to where we're talking here. There. Pretend I was able to do it nicely like that. So let me just erase my feeble attempt here. There we go. Pretend I was able to do it just nicely like that. You get the idea, right? Okay, so the amount of space in both of these circles is the same. So it's going to be 2 pi. It's going to be pi r squared, sorry. So how much space does a ring use? So the very largest possible ring that goes around the outside of this circle, of course, is the circumference of the circle. And yeah, pretend I could trace the circumference nice and cleanly like that. And the largest ring, of course, at the edge here, is also going to have a radius of r. So now, see if you can kind of imagine unrolling those rings. Like imagine if, and let me go grab another picture here. Imagine if you took a pair of scissors. There we go. And you cut along this line here. You cut along that line. And then you just unrolled them. Let me see if I can show you a quick, oh, that's interesting. That should have gone right to, oh, you know what? I bet it's because I'm in tablet mode. Let me go back. There we go. Let me show you what that looks like as a little animation here. There we go. Unrolling the rings. There, can you see that? There, nice little animation of that. Right? The outside one is 2 pi r, circumference of the circle. And the radius is, of course, r. And if you unroll all of those rings, what do you get? You get kind of a jagged triangle. So if I, again, let me grab a picture that I made here. So here's the rings, maybe in a little easier way to think about it. If I, let me drag, drag this over. Come on, there we go. So if I have the rings kind of easier to think about in this 2-color system, and or more than a 2-color system, and I kind of see, does this picture kind of make sense to you? Come on, this isn't working as good as I hoped it would. There we go. Come on, there we go. I unroll them and put them sort of together on an XY grid. I'm going to get something like that, right? If you take the rings, you get this sort of jagged upside down triangle. It doesn't have to be a right triangle. I do have another kind of version of it. Let's see, where is it? Oh, there it is. If you kind of imagine, there we go. I could think of it as taking all of, let me move up to this one, there we go. You could think of it as I take all of these rings, probably making people dizzy at home moving the screen so much, sorry. If I cut down here, then this inner ring here, this red one, is this little red strip here. This outside blue one is this outside one here. And once again, this is definitely going to be 2 pi r across the base and r for the height. And what's the area of a triangle? Well, the area of a triangle is 1/2 times base times height. So that's going to be 1/2 times the base, which is 2 pi r, times the height, which is r, and look where we're ending up. Area of a circle must be pi r squared. And again, there's going to be some skeptical thinking in your brain going, yeah, but that's not really a triangle. Look at all those gaps there. Look at all those white spaces. And even if I put it into a right triangle form like I did on this one, look at the gaps when I try to actually draw that as a straight line. But notice that the gaps would get smaller and smaller and smaller until they pretty much disappear if I make the rings infinitely skinnier. And this is, as it says in the notes here, going to be a recurring theme in our calculus. Big things are made from little things. And sometimes the easier things are easier, or sometimes the little things are easier to work with, and sometimes you can count them to infinity. And that allows you to get a value that isn't infinity. So that's kind of the theme of the first lesson, and that's kind of the introduction to what calculus is about. Okay, I'll stop the actual recording here. We still have a couple minutes. So let me just stop the recording. And come on, recording. Okay, thanks for watching.